So now that we've had a pretty lengthy discussion in previous lessons about derivatives, let's start looking at how we can leverage the information of what we know about a derivative and its graph to be able to determine the graph of the function. That is to say, let's start with this question. Suppose we had the graphs of f of x, or we had some function's graph. For example, suppose this right here. Suppose we were given this graph and we were asked, how could we determine approximate values of f prime of x? So looking at this question, at this graph here, the question is, how can we determine approximate values of f prime of x, or the derivative? Well, if we think about it, really what we're doing is we could just look at approximate tangent lines that we could graph and find the slopes. So we'll just go ahead and write that, and I've actually written it out already. What we're going to do is we're going to find the slopes of tangent lines, and we're going to plot them as points on f prime of x. So let's start with this exercise here. Let's actually try that here. So going back to this graph here, if this is my function f of x, I'm going to label this as f of x. Let's go ahead and let's try to sketch some approximate tangent lines, and let's try to find approximately what we think the slope of each of these tangent lines are. So let's start with a point like at, for example, let's say right around here, right around like 4/10 here. Because at this point, it kind of looks like our tangent line approximately, and I'll write this, m is approximately 1. That looks pretty close to having a slope of 1. And as we move along here, suppose we, let's say, chose an x value of 2, and I were to draw a tangent line right around here, can you kind of use those markers to give us a pretty good sense of what the tangent line's slope would be? And look, this looks approximately about like around 1/3, right? It looks like for every 1 unit that we're rising, it looks like we're moving over about 3, somewhere around there. It's not exact, but again, we're just approximating. And let's go with another spot, maybe somewhere towards the end here. So somewhere around here, if I were to draw a tangent line, this here looks like it has a tangent line of about, oh, I don't know, about 1/4, I would say it looks about right, moving up over 4. And we should probably also approximate a tangent line close to the origin here. Well, really here we can kind of see that as we get closer and closer to the origin, or as x moves closer to 0, that tangent line looks like it's approximately becoming pretty vertical. That is to say that our tangent line seems to be approaching positive infinity. Well, now that we have all this, what we're going to do now is we are going to take these tangent line slopes and we are going to plot them as points on our graph over here, because what we're trying to connect here is we know that the derivative gives us the slope of our tangent lines. So if I want to try to graph f prime of x, these tangent line slopes then are going to be y values or coordinates on our graph over here. So when our x value is about 2/5 right around here, it looks at like our m we said was about 1. So we would say right around here, that would be a y value of 1. When x was equal to 2, we said that our slope was about 1/3, which means on this graph over here at 2, I'm going to have a y value of about 1/3, which should be right around, let's see, right around there. And then as we get closer and closer to, as x increases, let's say towards 5, looks like we have something right around 0.25, which should be right around there. And we also said that as x gets closer and closer to 0, the slope of that tangent line appears to be going towards infinity. So graphically, we can graph something that looks like this, something that shoots up towards infinity here. And let me actually zoom in on this just so I don't have a little bit more space to draw. I can graph something that looks something like that. And it's not great, but again, we're able to still sketch a pretty decent approximation of how this function's derivative should be graphed. And we did that just looking at the slopes of the tangent lines. Now, what if I want to continue this process and graph the second derivative? What would we do then? Well, effectively, we would do the same process, but this time we would look at the slopes of the tangent lines of our derivative and use those and plot those slopes as y values for the second derivative graph. Now, let's kind of switch this around. This time now let's ask ourselves, well, okay, what about if I were given the derivative, and I wanted to go this way. Suppose I were given the graph of the derivative of f prime of x, and I want to be able to graph the function whose derivative is the graph that was given. What would I do then? Well, this is kind of intuitive for some people, but I know that others really benefit from having kind of a step-by-step approach to this, which I'll provide here. The first thing that I recommend doing is making an f prime number line. And I'll just write that, an f prime number line, or a number line for our derivative, using the location of points on the f prime graph. And then I'm also going to make a second derivative number line using the slopes of points on the f prime graph. And we'll do all this in a practice problem in just a moment. And then we're going to use both of these number lines, use both lines to sketch f of x. So let's try an example of this right now. So if we look here, take a moment and kind of examine what's being given here. We are being given the graph of f prime of x. We were given the graph of the derivative. And from here, we're going to sketch an approximate graph for the second derivative. And then we're going to graph the original function, f of x. And I'm giving you a specific point that I'd like it to go through when x is 0. I would like y to be 1 there. And we'll discuss in a moment why that might be somewhat important. So let's look closely at this f prime x graph real quick. So this is, again, the graph of the derivative here. Let's make sure we understand what's going on. And it might be helpful to draw our f prime number line underneath as we go along. Okay, let me redraw that line. Okay, so looking at this here, well, what do we notice? We notice that our derivative crosses its x-axis at -2. Well, think for a moment what that means. This means that our original function f of x is going to have a critical number at -2. So at -2, we see that our derivative changes signs from negative to positive at -2. Therefore, -2 we see is a critical number. And specifically, actually, we can take that a step further. We know that -2 is the x value that causes our derivative to be equal to 0. And so if our derivative is equal to 0 and there is a sign change, that means there's a change in behavior. This function goes from decreasing to increasing. Therefore, this point -2 here is also a relative minimum that will have a tangent line that is horizontal, with a horizontal tangent line. Okay? Well, what else do we know? We know that when x is equal to -4, our slope, the slope of our function at -4, is going to be equal to -2. Okay? When x is equal to 0, the slope of our function is going to be +2. Okay? So we'll come back to all this, and we're going to use all this information to sketch our f of x in a moment. But let's take a moment and let's think about how we could use the graph of the derivative to graph the f prime number line. So let me actually do that. So we have f prime here. So we're going to sketch. Let me actually do that again. So this is the f prime number line now. So now what we're going to be looking at are the slopes of my derivative. What does the slope of f prime of x appear to be from -4 to 0, or from -infinity to 0? Well, it looks like the slope is +1. Okay, it looks like the slope is +1. Hopefully we can see that here. It looks like we have a rise of 1, a run of 1, so the slope appears to be 1, and it's going to stay being +1 all the way up until 0. So from -4, or -infinity to 0, I should say, we can draw a horizontal tangent line. All of the y values up until that point are going to be +1. Okay? Now, what about after that? Well, again, if we're looking at the slopes of the tangent lines here, we can start graphing. Well, at x is equal to 0, it looks like we have a horizontal tangent line. So that means our slope would have to start here at 0. But after that, the tangent lines start to increase. And they stay kind of flat early on, but they start to increase pretty dramatically after that. The main thing that we have to understand here is that the tangent line slopes are changing. They're not going to be constant. So we can kind of estimate something around here. We can say right around here, it looks like our tangent line is about 2. So at 1, we can say it seems to be hitting about 2. So we can graph something that looks like this. That would look like that. Now, important note, back here at x is equal to 0, is that point differentiable? And the answer is no. We appear to have a sharp turn. That is to say the left and right-handed derivatives wouldn't quite agree. So there we would be able to draw holes if we needed to. So I'm going to just kind of draw this as a hole if we can. But now looking at this f double prime number line, let's kind of, or this f prime double prime graph, let's look at what's going on here. From negative infinity up until 0, which is a possible inflection point, we see that our second derivative is positive here. Therefore, it's concave up. If our second derivative is positive, then it's concave up in this interval. From 0 to positive infinity, we see that our second derivative is still positive. So there are no inflection points here in this graph. Because there were no points where the second derivative changed signs, there are no inflection points. This graph is always going to be concave up. So we've broken down what we know about the second derivative. We've broken down what we know about our first derivative and its implications on our function. So we're now going to put everything together. We're going to kind of combine the knowledge that we were able to glean from these two graphs and now try to graph the original function. So let's do that. So I'm specifically saying that f of 0 must be equal to 1. And we'll come back to that in a moment, but we'll say that. Now, what do we know? This is kind of the reverse engineering of what we did here, where in this previous problem, I gave you the graph and I asked you to sketch tangent lines. Now imagine instead, I had just instead given you a bunch of tangent lines and I wanted you to kind of flesh out a function that matched those tangent lines or fit underneath those tangent lines. Well, that's sort of what we're doing here. So we could say that here at -4, we know that our tangent line is -2. Well, actually, let's start at 0. That might be a little bit more helpful. We know that at 0, the slope of our tangent line, we said, was +2, which would mean it should look something like this. And that appears to be a tangent line with a slope of about +2. And we know that at -4, our tangent line, or excuse me, at -2, our tangent line is 0. So what we're seeing here is that these tangent line slopes are going to change until -2, it would kind of flatten out. So we need a tangent line of about 0 right around down here. Now, do I know it's exactly down there? Not quite, but I'm just sketching something out. And then as we go to -2 or -4, our tangent line has a slope of -2. So I actually want to graph something that looks to be going this way. And since again, I saw that the rate at which my tangent lines were changing remained the same. It was constant, it was linear, our derivative was linear here. That then gives me a sense that this graph, if I were to graph something that kind of matched these tangent lines, I should get something that looks like this. And if we even take a step back on that note, if my derivative is linear here, if this derivative is linear, that means my original function had to be quadratic. But hopefully that kind of makes sense how I can use my tangent lines to sketch out a graph and see what's happening here. Now let's finish it up. We know that after 0, the tangent lines start to, the values for f prime of x start to increase. So what we would see here is that this graph starts with a slope that's pretty low and then starts to dramatically change. Start to approach something that looks like this, okay? This is a little bit of a unique function in that since this was linear here, but you'll notice here this is quadratic. So this is actually a piecewise function that is a combination of a quadratic and a cubic function. So despite this looking like a parabola, it's actually not. If I were to kind of continue this on, you would see that this would follow more of the behavior of a parabolic curve, and this would actually start to shoot up, similar to like a cubic function here. Now on that note, I should say that this anchor point of f of 0 being equal to 1 was actually pretty important because without this information, I could have technically drawn a curve that looked like it was here, or potentially something that looked like it was here. There are a lot of places where I could have graphed this. In fact, there are an infinite number of places where or ways that I could have vertically shifted this function here. And we'll talk more as we move forward about this idea of coming up with a function whose derivative is what we know. And this idea here that we're kind of hinting at is the idea of an antiderivative, and understanding that an antiderivative actually gives us a family of possible functions. Now, the last thing I do want to highlight about this question, since it is a little bit interesting, is that this is technically not a sharp turn here. That is to say, this point here is indeed defined. So this point f prime of 0 does exist. F prime of 0 exists or is defined. That is to say here that this is not a sharp turn necessarily. Even though we're going from a quadratic to a cubic, if without kind of giving the detailed functions here, I might as well write it out. This piecewise function actually is 1/2 x plus 2 squared minus 1. And this function here, we'll just call this g of x, is actually 1/3 x cubed plus 2x plus 1. And if you evaluate these derivatives here, you'll see that these derivatives, both of these derivatives evaluated at 0, both give you the same y value of 2, in which case that would indeed, we would be able to draw a tangent line there. So we would not consider that a sharp turn. Okay, so let's try one more example here of something similar to this. Take a look at this function here. And there's actually a little bit of a typo. I should say that f of 0, I want that to be -1 here. So let me move that here. But the problem in this case, again, I'm giving you the graph of the derivative. I would like you to sketch the derivatives or the second derivatives graph, and then use that information to sketch the graph of the original function, f of x. So pause the video and try that real quick. Well, if this is f prime of x, and maybe I should just highlight it instead of writing that a little bit again. Let me go to a different color now. If that's f prime of x, we know that the slope of the tangent line here appears to be 0, and we can also see a horizontal tangent line around here. At the origin, it looks like our tangent line has a slope of about 1. And then similarly, at these points, we can see that the slope of the tangent line appears to be about -1. So if I were to sketch those slopes of those tangent lines as y values, I would see that this would be -1. Right around here would be about 0. This would be +1. This would again be about 0. And this would be about -1 right around here. So this graph would actually look something that looks like this. And you probably figured out what function was being initially given here. F prime of x, if you could tell, is actually the sine graph. And what do we know about the derivative of sine? We know then the derivative of sine is just cosine. So the second derivative here is cosine of x, and that seems to match up with what we have graphed here. And now we can take that information and we can graph the original function. Let's just do that in blue. Well, that would look now something like this. If I have to go through 0, -1, I would actually get something that looks something like this. And you probably figured it out. We know that if f prime of x is sine x, that means f of x would have to be negative cosine x, which is exactly what we've graphed there. Okay, so hopefully this has helped you develop an understanding of how to actually leverage the information from the derivative and the second derivative to come up with a graph for the original function.